All right, in this section we're going to expand what we know about exponents. We already know how it's defined, right? This the basic idea of a to the n power means that I'm taking the base a and multiplying it by itself that many times. Right? We have n factors of a. We got some nice properties of exponents that can allow us to simplify expressions. So if I'm multiplying two exponential expressions that have the same base, then I can add the exponents. So, for example, 7 to the 6th power times 7 to the 13th power is 7 raised to the 6 plus 13, or 7 to the 19th power. If I'm dividing two expressions with the same base, then I can subtract the exponents. So x to the 12 divided by x to the 8, that's x to the 12 minus 8, or x to the 4th. If I'm taking an exponential expression and raising it to another power, then we can multiply those exponents. So y cubed all to the 8th is y to the 3 times 8, or y to the 24th power. And if I'm multiplying inside a set of parentheses and raising that product to a power, then we can distribute an exponent over multiplication. So 3x to the 4th, this is multiplication, right? 3 times x, and that's being raised to the 4th. This is 3 to the 4th times x to the 4th, which gives us 81x to the 4th. We can also distribute an exponent over division. So if I have a fraction that I'm raising to a power, we just raise the numerator to that power and the denominator to that power. So this is, in this example, 2x over y all cubed. This is 2x cubed over y cubed. And up top I have a product raised to a power, so I got 2 cubed x cubed over y cubed. And then we can simplify that to 8x cubed over y cubed. You'll notice here, going from the starting point over to this spot, basically if everything is multiplication and division, right, there's no addition or subtraction happening in that original fraction, and I'm raising that to a power, essentially all, each individual factor gets raised to that power. And then the 0 exponent. If our base is not 0, then a to the 0 is equal to 1, always, for any non-zero base. You just want to be careful that you are aware of what that exponent is being applied to. So over here I've got two examples. They look really similar. First, we have 1.2 pi in parentheses to the 0. So it's the whole 1.2 pi being raised to the 0 power, and so that'll give me 1. Down here I have 1.2 times pi to the 0. 0 exponent is only on pi in the second expression, so this is 1.2 times 1, or 1.2. And I can convince you, like sometimes people are confused that something raised to the 0 power should be 1, but I can actually convince you that that is true with a simple example. So let's say I would take 2 cubed and I divide it by 2 cubed. On the one hand, I'm taking something and I'm dividing it by itself, so I know that should give me 1. On the other hand, I have the same base, right, raised to powers, and I'm dividing. So if I go up here to the second rule, I know that I can just subtract those exponents. So bringing that down here, this is 2 to the 3 minus 3, or 2 to the 0. And of course you could write an example like this for any non-zero base. And then last, working with negative exponents, a to the negative n is defined to be 1 divided by a to the n. So 8 to the negative 2 is 1 over 8 squared, or 1 over 64. A negative exponent does not make something negative, it just makes it small. And that's something that we really want to remember and keep in mind. And when we write a to the negative n equals 1 over a to the n, we think of this as saying, oh, I'll just put it in the denominator, but it actually works in both ways. If I have a fraction 1 over a to the negative n, this is a to the n. So it just sort of changes the position, whether it's in the top or the bottom. It just flips it, it moves it, and then you change the sign of the exponent. So, for example, 1 over 8 to the negative 2 is 8 to the positive 2, or 64. Now we saw in the last page that we can distribute an exponent over multiplication and division. We should be really careful and note that we cannot distribute an exponent over addition or subtraction. Be really, really mindful of this. This is a really common mistake to make, no matter how many times we might make that mistake and kind of learn again, oh right, I'm not supposed to do that. People just really want to be able to distribute an exponent over addition. I mean, that I guess would make some things easy, but we're just not allowed to do that. And to show you why, to convince you of this, we'll do this quick example. 3 plus 4 squared. Now we know the order of operations. The order of operations tells us that over here on the left side, I have to do the addition first because it's in parentheses. So 3 plus 4 is 7, so this is 7 squared, and that gives us 49. On the other hand, if I had the sum 3 squared plus 4 squared, order of operations says, I'm going to apply those exponents because there are no parentheses. 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25. And we know for sure, it takes no convincing, we know for sure that 49 is not equal to 25. So 3 plus 4 squared is not equal to 3 squared plus 4 squared. We cannot distribute an exponent over addition. This is just one example, but one example is all you need to show that something is generally not true. So just be really mindful of whether you have some addition or subtraction happening in your expressions. We're going to do some examples here, simplifying these expressions. So we begin ax squared times ax cubed. So the ax is in parentheses there. And the first thing I'll do is apply this expression, or that property that says I can distribute this exponent over multiplication. So I've got ax squared times a cubed x cubed. And now I'm going to rewrite this because multiplication is commutative. That means it doesn't matter what order we write the factors in. So I have a times a cubed times x squared times x cubed. And that first a here in the beginning, there's no exponent written, but it's understood to be 1. A times a cubed is a to the 4th. I can add those exponents. X squared times x cubed is x to the 5th. I can add those exponents. And that's our final result. Next, we have this fraction, and I've got some stuff going on, right? We have a parentheses raised to a power up top, and I've got a product there raised to a power. So I'm going to distribute that square. So we have r squared times y cubed squared. On the bottom, r times y cubed to the 8th. Now, we can use that property that says if I'm taking an exponential expression like y squared and I'm raising that whole thing to a power, I'm going to multiply those exponents. We get y to the 8th. I'm going to do the same thing right here. So now up top we have r squared y to the 6th over r y to the 8th. On the bottom, that r is an r to the 1st, and we can just reduce this fraction. You could think of it as canceling common factors, and you could think of it as applying the rules of exponents by subtracting. I'm going to show you both ways. If I just think about subtracting exponents, then I end up with r to the 2 minus 1 times y to the 6 minus 8. So that's r to the 1st times y to the negative 2. And if I don't want to use negative exponents in my result, and usually we don't, I'm going to go back to writing this as a fraction, r over y squared. So there's our result. Alternatively, I could start here and say, okay, I've got r squared times, or actually let me write it as r times y to the 6. On the bottom, I have r times, and that y to the 8th I'm going to write as y to the 6 times y squared. right? Certainly I know if I were to add those exponents, I get myself back to y to the 8th, and we can cancel the common factor of r, we can cancel the common factor of y to the 6th, and we get r over y squared. So regardless of how we want to look at it, how we want to apply the rules of exponents, and think of it as reducing a fraction or subtracting exponents, we'll get the same result. Okay. Our last example, we have this fraction, a whole fraction raised to a -2 power. So I'm going to do a couple of things here. To start, I'm going to think of this just as a fraction to a power, so I'm going to distribute that -2 exponent to the top and to the bottom. So a cubed times t, b squared times x. Next, I know that if I have a negative power, now there's more than one correct order in which you could apply these properties. I'm going to just show you the way I'm thinking about it. I've got these negative exponents. So a negative exponent means I'm going to just pull the expression, or just move the expression from the top to the bottom, or vice versa, and change the sign of that power. So this is going to move down here, and we're going to write it as a cubed t to the +2. And this is going to move up here, and we're going to write that as b squared x to the +2. Now I'll just address the fact that I've got a product to a power in the top and in the bottom. So I got b squared squared times x squared. In the bottom we have a cubed squared times t squared. And then the last thing is, when we're raising a power to a power, we're going to multiply those exponents. So we have b to the 4th x squared over a to the 6th t squared.